The next component of the mole concept is actually looking at something slightly different, which is called percent composition. And percent composition is a reflection of how much of the compound is made out of each particular element. So John Dalton's law of definite composition or proportion states that the same compound always contains the same number of atoms of each element and in the same proportions. If we happen to look at this statement, it makes a lot of sense because we have the words definite meaning constant, and proportion, and we know from math that a proportion really means a ratio or a relationship. So we can have 1 to 1, for example, or 1 to 2. So you always have that same constant ratio of elements in the compound. John Dalton derived this law by carefully decomposing several different compounds from several different sources and by finding the percent composition by mass of each element. In so doing, he found that the ratio of the masses of the element, again, that's the masses of the element in the compound, is always the same. Now, just to review, when we talk about a percentage, what does that percentage actually mean? Well, I always think about a percentage as reflecting the same thing. If you had a percentage in the class, it represents the part of the whole that you achieved in the class. So to find the percent mass composition of a chemical compound, we have to, 1, calculate the molar mass of the compound from the chemical formula. Remember that that just is the sum, that means that you add them, of the elements' masses and that's taking into consideration the proportion of them. So if there's 2 hydrogen, you need to multiply the hydrogen's mass by 2. If there's 5 oxygens, you need to multiply the oxygen's mass by 5. Then you calculate the mass of each element present based on the molar mass calculation. So don't forget the subscripts again. Again, if there's 2 hydrogens, there's 2 hydrogens contributing to the total mass. So you've got to times the hydrogen's mass by 2. Again, if there's 5 oxygens, you have to times the oxygen's mass by 5. And then we use the formula, but it really is just a reflection of what I've already told you about a percentage. It's a part of a whole times 100. So we take the mass of the element, that's the particular part that we're interested in, divided by the mass of the compound, that's of the whole compound, and then we multiply it by 100 to get to a larger value. So let's look at calculating the percentage mass of water. And just to remind you, water is H2O. So the first step that we have to do, and I'm just going to change ink colors here, is to calculate the sum. That's what that fancy symbol means. The sum of the elements' masses. And I'm going to lay this out in a particular format so that it makes the later steps easier. So we know that there's 2 hydrogens. So that means I have to take 2 times the mass of hydrogen, which is 1.01, and multiply it together to get 2.02. The units there would be grams per mole. So the part of the mass of the compound that hydrogen is contributing to is 2.02. We know that there's 1 oxygen, so I take 1 times the mass of an oxygen, which is 16.00, which gives us 16 grams per mole. Notice again that that's the part of the mass that oxygen is contributing to the compound. So looking at adding that up, because we said it's the sum, it's the total mass of the compound, the entire compound was 18.02 grams per mole. So that's step number 1. Step number 2 is that we have to consider how much of the mass did each particular element contribute to the entire compound. So when we look at the percentage of hydrogen and the percent of the oxygen, remember it's just the part of the whole. So the part of the mass that came from hydrogen was 2.02 grams per mole. and that's of 2.02 grams of the entire 18.02. That's our whole. And in order to change it into a value which is not a small decimal, we need to multiply that by 100. And that value gives us 11.2%. Looking at the percent oxygen, again, it's the part of the whole. So the part of the mass that came from oxygen is 16 grams per mole. I need to divide that by the entire molecule's mass, 18.02 grams per mole. And again, I need to multiply by 100 because we multiply all percentages to get a value greater than 1 most times, and we would get 88.8%. Now, when we look at those two values, I want you to notice, what did the sum of the two percentages work out to? Well, 100%. And that should make a lot of sense. If you add up all the parts that were available, you get 100%, the entire thing. When we look at percent composition, I just want to highlight that the convention for this is that you always go to one decimal place. Okay, so we always report these percentages to one decimal place. That's a convention that you should know. Hint, hint. So now I'm going to ask you to actually do some practice problems from home. I'm going to give you the question, and notice I'm already even giving you the molar mass of the entire compound. And then you can pause the video long enough to try and attempt the question on your own, and then I'll report the answer. So the first one that we're going to look at is dinitrogen pentaoxide. Remember, we do have to remember the names of these things. And it has a molar mass of 1.08 grams per mole. So now I need you to calculate the percent of the compound which comes from nitrogen and the percent of the compound that comes from oxygen. Okay, looking at our answer, we look at the part of the total that comes from nitrogen. There are 2 nitrogens, each of which contributes 14 grams per mole. So the total part that comes from nitrogen is 28 grams per mole of the whole molecule weighing 108 grams per mole. We multiply by 100 to get a value greater than 1. And in this case, we get 25.9. Now, for those of you that have already put this together, you could certainly look at it and go, okay, well, if 25.9% is nitrogen, then the remaining 74.1% should be oxygen. And although that's true, I would prefer that you actually go through and calculate it. So you've got that little fallback double check for yourself. And just to confirm, yeah, that's exactly the way it works out. So we have 5 oxygens, each of which contributes 16 grams per mole of the entire whole molecule, which weighs 108 grams per mole, multiplied by 100 gives us 74.1. Okay, next practice problem is looking at the percent composition of aluminum chloride. And unfortunately, notice this time I didn't actually give you the formula. So you need to figure out the formula of the compound first, and then calculate the percentage that comes from aluminum and the percentage that comes from chloride. So before you start your actual calculations, we need to remember again, aluminum chloride is Al, which has a 3+ charge, and Cl, which has a 1- charge. That means I need 3 of the chloride ions in order to balance out the 3 positive charge. Now looking at the calculations, I know that I have 1 times the mass of aluminum, which happens to be 26.68. Of the whole molecule, 133.33 grams per mole, and multiplying that by 100, I get 20.2. Now doing the opposite calculation, we've got 3 chlorides, each of which weighs 35.45, of the entire molecule, which is still 133.33 grams, multiplied by 100 to get a value greater than 1, and that gives us 79.8%. Again, looking at the percentage values, they round up to, or they add together to produce 100 as a total. Okay, next one we see is sulfur dioxide. Notice this time we have a covalent compound, not an ionic compound. So that means that you have to consider that these are neutral atoms. We disregard charges on the periodic table, and that's why we've got the prefixes. So it has a molar mass of 64.07, and I need you to, 1, figure out what the formula for sulfur dioxide is, and then calculate the percentages. Sulfur dioxide has a formula of S. If it doesn't have a prefix on the first one, it's just a 1. And dioxide means that there's 2 oxygens. So looking at the percentage, I know that there's 1 times the mass of sulfur, 32.07 grams per mole, of the entire molecule's mass, which is 64.07, and multiplying that by 100, I get 50.1%. For the oxygen, I take 2 times the mass of 16, gives us 32 grams. That's what the oxygen, the part that oxygen is contributing to the molecule, divided by the whole molecule's mass, 64.07. And when we multiply that by 100 to change it into a percentage, we get 49.9%. Again, the sum of those two percentages adds up to 100. The last particular one that we're going to do is actually a tricky one because it's looking at nitric acid, and we didn't actually go through yet the naming for acids. But what I can tell you is that if you look at an ic acid, that comes from an 8 ion on the periodic table. So in this case, that one is nitrate. And then to make it an acid, we throw on as many hydrogens as we need to balance out the charges. Hydrogen has a 1 plus charge and nitrate has a 1 minus charge, so nitric acid is HNO3. Now I want you to calculate the percent composition, but you'll notice now we have 3 different types of atoms, so you have to calculate the 3 different percent compositions. So the percent value for hydrogen is 1.01 because there's just 1 hydrogen of the 63.01 grams per mole. Multiplying it by 100 to change it into a percent, we get 1.6%. Looking at the nitrogen, there's also again only 1, so we get 1 times its mass, 14, of the entire molecule, of the whole molecule, 63.01 grams per mole. Multiplying by 100, we get 22.2%. Just like before, all of the percentages should add up to 100, so let's check for oxygen. Now we have 3 oxygens, each contributing 16 grams per mole, so that contributes 48 grams per mole of just the oxygen. Of the entire thing, the whole mass is 63.01 grams. So when we multiply that by 100 to get a percentage, we get 76.2%. And in fact, those do add up to make 100%. Now that's actually where we're going to leave that for today. And we'll work more with this in class next day.